Hey guys, welcome back to another Leetcode problem solving tutorial, and in this tutorial I'm going to be showing you guys how to solve question 297, asking you to serialize and deserialize a binary tree, or essentially just convert this tree object into a string. That's what serialize does, and then deserialize takes in this string as just some data and then manages to convert it back into a tree object, so in terms of tree nodes. So yeah, obviously you can see the uses of this. If you have a tree stored and then you need to sort of serialize it so that you can send it somewhere, then this needs to be used. Leetcode actually uses this in all their problems when they pass in an input for the root, because this is in serialized form, and then they obviously pass it in as a tree node object, but here they've just got it in serialized form. So I'm going to be showing you guys how to do this, and it's actually fairly simple for a hard question. We just need to understand that when you serialize and deserialize objects, the most important thing is consistency. So you got to serialize them in the same way as you deserialize them, and the other way around as well, to make sure that all nodes end up in exactly the same spot as where they were. So let's look at this tree as an example. So it has 1, 2, 3, 4, and 5 as nodes, and they are connected just like this. And yeah, the idea is, so we're going to start at 1, and we'll use this as our starter node for the string, and then we need to take the left and right nodes, but we're going to be using depth first search, so depth first search, it traverses the left, then traverses all the way to the left and then the right in the same node, and then it goes back up, traverses the right, then it just keeps going left wherever it can, and when there's no more lefts it goes right, then goes up, and then goes to left and checks like that. So it's essentially calling the left and then right in a recursive manner. And remember, when it's recursive, it doesn't just mean there's going to be one left and then check the right. It means it's going to go left. If this one has a left, it's also going to go left, and it's just going to keep on going left until there's no more lefts, and then it'll check all the rights on the way. So that's the idea of depth first search. We're going to be using it, and it's quite a standard algorithm, so make sure you understand it. But yeah, so we'll add this 1, then what we'll do is we will separate it and add this 2, and then the important thing is to uniquely identify a binary tree using a string or serialized form, you need to also include the null nodes underneath each of these nodes. Because if you just have a generic pre-order travel, which is what depth first search is, a generic pre-order travel, that's not actually going to be able to uniquely identify a binary tree. And there's actually a question on this in Leetcode, which gives you a pre-order travel and an in-order travel and asks you to uniquely construct that tree, because the pre-order alone without the null nodes isn't enough. So we get to 2, we know there's a null node on the left and a null node on the right, so we'll just use X to mark out these nodes, or we can use N for null, doesn't really matter. But yeah, once we've added these null nodes in, then we're going to go back up the tree and back to 2, and then back to 1 since it's completed everything on this side. Then we go to 3, add in a 3, and we go to the left. We have a 4, and then we have 2 null nodes like this. So null, null, back to 3 now, goes to 5. I'll just go down over here. And then again, we have 2 null nodes on either side, like so. So this is what our final string would be when we serialize it. And I'll explain how to deserialize this in just a second, but first let's implement this fairly simply. So we'll just take this function in, serialize, and we're going to have some sort of array, so I'll just call this an array of, we'll make it an array of strings, doesn't really matter, but, or not even an array, we can just store this as a simple string actually. So we'll call this serialize string, make it a let since we're going to modify it, and yeah, we're going to use some commas. I'm just trying to think of a function, so if we have an array like 1, 2, 3, just trying to think of a function which sort of adds it. Okay, yeah, so we can just use a join function. Okay, so let's store this in an array. Sorry, it's storing a bunch of strings for each number, because remember we want to return a string, so it's probably best if we store them as strings in the array. And this is just going to be storing this. And what we need to do is we're going to create a depth first search helper function, and all it takes in is a simple root tree node or null, and it just adds this data to the array. So if the root is equal to null, for example if we were here, then we just add a n to the array, so just add that there. Otherwise we can just add the value to the array, so root.val, and of course we need to convert this into a string. Now that we've done that, no need to check this since we can just return from here. And yep, so we've checked if it's null. We've added the current value, but then remember we need to also add array.push, and not even array.push, we can literally just repeat this but for the left and right nodes, so root.left and root.right, like so. And that's what I was talking about depth first search. We go left first and then right. So how this would work, if we pass in this 1, it adds the value of 1 to the array, then runs depth first search from the left, and then we'd add 2, depth first search on the left again, but this time it's null, so we add n to the array and just return, so no more recursion. And yeah, that's essentially how it works. So pretty simple algorithm, and all we have to do is run this on the initial node like so, and then we can just return array dot join, and we'll use the comma separator. Okay, there we go. So here's our serialize function. Nice and easy, pretty simple. We just had to serialize this. So now the deserialize function, because there's no point just writing one without the other, right? And just put it over here. Actually, let's separate this with 3 lines so it's a bit clearer. Okay, so deserialize is going to give in this data as a string. And the first thing we obviously want to do is convert this data back into an array. So I can just do something like, well, let me just have a look at what this does. Yeah, so this join function is just going to return this kind of string. So we can get the array back by just doing array equals data.split on the comma, like so. And this is just going to give us an array with all of this. Nice and easy. Of course we could have just used JSON.stringify and JSON.parse, but those are only really found in JavaScript natively, so that's why I've used a more sort of regular approach here. But yeah, if we're going to give this array, how are we going to reconstruct this original list? Well, obviously the first item is going to represent the node, and yeah, we can just do the same kind of thing. So if we use depth first search again, go to the left, and we basically keep track of which index we're on. So let's say this is the one we're currently on, and when we've added this, we add 1 to the index. So now we go over to here, and we run depth first search left onto this, and once you've added this as a node, we run depth first search left again, because remember that recursive nature keeps going left. So we know the index is here in the array, and we're currently at this node, and we add none there. Now if it's none, we just need to stop that recursion, but we still add 1 more to the index, and at this point, so this has triggered the left, and now by this time there's nothing left on the left, so the right is going to get triggered, and that's where this comes in. So this gets added. Again, it's null, but we still add 1 to the index. And by this time, we've added all the nodes on the left side, so there's nothing left within this sort of recursion stack. So it goes back to the 1. Remember, 1 was going from 1 to 2 on the left, but now there's nothing left on the left. So we go to the 3 on the right side, adds in the index at this node for the right of 1. adds 1 to the index, and then we use the left here to give us 4, left again to give us n, and when it's null we return. So it brings us back to where this for function call was, brings us to right, and index has been incremented. We add this, and now left, right have both been null, so we return back to this for. We've completed both these left and right calls, so this function gets returned back to the free. And yeah, this free then executes its right. Sorry, that was a pretty bad arrow. Let me see if I can just do this. Okay, that's good enough. So yeah, this is its right now. We've executed this function. Now moving on to the right, index incremented to 5, and again we go left and right, like so, and just add in these items. So hopefully you can see how we're utilizing the fact that this is a recursive function and just goes left continuously and then right, using the consistency between these, because we're going to implement a similar function here. And I'll just call this one, actually we need to start off with a root, so we'll start off with, let's see, yeah, okay, we don't actually have to start off with roots, so we're going to be returning roots here rather than just adding them to an array, so we don't actually have to start with anything. But I'm going to call this depth first search construct, because we're going to be depth first searching, but we're also constructing nodes as we do it. And the parameters for this is pretty simple. We don't actually need anything because we've got the array as a global variable. We're not taking in any sort of nodes, and yeah, we're not doing any of that. The only thing we'll keep track of is we'll keep track of the index, just so we can loop through this array. Depth first search construct, so we're not actually going to take in any parameters. And what we'll do is we'll use this index, so we're checking if the index at position in this array is going to be null, then we want to add 1 to the index, of course, index plus equals 1, but we return null. This is kind of like, if you see later, we're going to be doing something like root.set, we'll do root.left is equal to depth first search construct, and we don't pass anything in, but its index is implicitly getting changed, and if this is going to be null, like for example here, then it's just going to set this equal to null, which is what we want. So there's the sort of base case, and then the recursive case is, well, let's create our root. It's just going to be, or call it a node, and it's just going to be a new tree node. Value is going to be the number of array of the index at position in the array, and we can just leave these two undefined for now. Doesn't actually matter. But what we're doing is, once we've added the item at position index to the array, we need to add 1 to index so that it moves along for the next item to be added. And then what we're going to do is we're going to set node.left is equal to depth first search construct. We added 1 to the index, so we don't have to worry about this. We don't have to worry about this being the same index because this is added 1. So it's kind of like if you were here, you add 1 to get to this position in the array, and then you're setting left to be this, which is going to return null. And do the exact same thing for node.right. Don't worry about these. Once you've constructed this node, remember this is going to work recursively. So this is going to get called, then this entire thing is going to repeat until it keeps on returning null, and then it's going to go back to the start. Once we've done all that, we just return a node, and that's nice and simple. So here's our depth first search construct function, and what we can do is we've initialized the index to be 0. We just have to return depth first search construct, because this is going to start creating a node from index 0 in the array and repeat until everything returns null and we complete this final array, this initial function call. So yeah, that's how that works. That was how I complete Leetcode question 297, serializing and deserializing a binary tree. It's a pretty cool question actually. And yeah, let's submit this, see if it works first of all, and then see if we get a good time complexity. Okay, there we go. So we do get a good time complexity. You can see we're beating 99.39%, so that is top 99 percentile, or top 1 percentile, however you want to say it. But yeah, pretty sure the reason this is fast is because of the simple recursive nature of this, and also the fact that we're not using JSON, rather just joining it. That might contribute. But if we look at here, right, so these guys haven't really done it properly. Again, they're utilizing JSON. So yeah, there's actually not many people doing it legit up here, but we have, this one's done it legit. So same sort of thing, depth first search. If node is null, then we just push null into the thing, and then we otherwise push this and use left and right, then join it with comma, and this is looping through the index, incrementing, and yeah, so same sort of thing, and we just depth first search to create the list, and then depth first search here to get the list into the form of a tree. Thanks for watching, and that was Leetcode question 297. See you guys in a future tutorial. Bye.